So I really want to maximize kind of our time here and kind of do our best with it. So what are some things that we need to talk about, want to talk about?
I'd like to learn more about like the naming. That's what I have issues with.
Okay. I mean, naming's a big part of this exam. So are we talking organic naming or?
Yeah, with like aldehydes, ketones,
Okay.
you know, all that.
Okay, so let's see if we can find some, maybe this is not the best way to do it. Pull up the ebook here. So, you know, the best course of action, the best way to do any of this is we just have to spend some time with it and just practice it. And I know you've been practicing. But we just have to keep going and keep practicing and keep trying to do more. So, you know, if we're looking at a problem like, well, let's look at number 56 here. Give the IUPAC name for each of the following. So, you know, what we have to do is, you know, we have to look at, start from basics, find that longest chain, figure out how many carbons are in it, try to identify any functional groups that are present. So I can look at this and say, okay, there are 1, 2, 3, 4 carbons in this chain. I know I'm dealing with a butane of some kind. But I also can recognize that I've got this carbonyl group here, this functional group, which, since it's not at the end of the chain, we know that this is a ketone. So I'm not dealing with butane, I'm dealing with butone. Or to clean it up a little bit, butanone, where we just add that extra syllable to it just to kind of make it a little bit more friendly. So I've done the first thing that I'm always asked to do. I find that longest chain, I identify the functional groups, and now I just need to make sure that there isn't anything else. And there isn't. So now it's just a matter of the location. And in the case of butanone, it's always going to be in the 2 position. It can't be anywhere else. If it's in the 1 position, it wouldn't be butanone, it'd be butanal. And positions 3 and 4 are just mirror images of positions 1 and 2. So this is one of those examples where we don't actually need a number for the functional group because there's only one place that it can be. So very similar to when we do, you know, cyclohexene, for example. If I have a cyclical hexene that's not benzene, I just call it cyclopentene, cyclopropene, cyclobutene, because that double bond is going to be in the chain, in the ring, and the only place it can be is in positions 1 and 2. Can't be anywhere else. So in the case of butanone, we're done. That's it. Now, what about this second example? Now, in the second example, we've got a lot of different groups in it. So let's just kind of identify them one at a time. The thing in the middle, what is it? That's benzene. So we know we're dealing with a benzene substance. We're dealing with an aromatic. Remember, aromatics are just benzene and benzene derivative compounds. So now we can look at it and say, okay, what is attached to this benzene? Well, I can see that I have this group here, and I also have these two groups. So those two are the same. So what do I do with it? Well, I have to figure out which of these functional groups is actually the most important. And anytime we see a carbonyl, we know that that's the most important one. So what is this functional group?
Aldehyde.
That's an aldehyde. I've got a carbonyl on the end of a chain. And I know it's the end of the chain because I've got that hydrogen group there. So I've got an aldehyde. And I also have these chloro groups. There are two of them. So I know that it's going to be dichloro. And I also know their position relative to the aldehyde. The aldehyde is going to be in the 1 position. They're evenly spaced. 2, 3, 4, 5, 6 would be the numbering. And if I numbered in the other direction, I get the exact same thing. 3 and 5 are the positions of the dichloro. So now it just becomes a matter of, I've identified all the functional groups. I just need to figure out how to put all of this together. So I started with benzene. I'm going to end up having to change the name of benzene to benzaldehyde to reflect the aldehyde group on there. So this is one of those where we don't change it to Al because it's not an alkane. If it was an alkane group, we would just change the ending to Al. Here, because we've got an aromatic, we're just going to slap aldehyde on the end. So I've got benzaldehyde, and so that covers the benzene ring and the aldehyde group in the 1 position. And now I just need to add the 3,5 dichloro to the front. And there's the name of my compound, 3,5 dichlorobenzaldehyde.
So in that kind of situation, you wouldn't have to put like the 1-benzaldehyde.
Because the aldehyde is assumed in the 1 position. The only time we would have to number it is if there was some kind of a question about where it would be or what the relation to it and the other groups would be. Since we're dealing with a ring here, we don't have to.
Okay.
We don't have to do that. So I know the one example that we did in class where we had, I think it was maybe a ketone and a chloro group on it. Well, the reason we had to deal with it that way was because we had to establish the relationship between where the carbonyl and the chloro was. And so I couldn't just position the chloro group without also giving context to where the ketone was.
That's what
Jenna?
I did.
So like when you have multiple different substitutions, I know this one doesn't, but like how do you know when to alphabetize them and like where to simply
Okay, so numerically speaking, we will always alphabetize and we will always number based upon those alphabetics. The only time that the alphabetics don't come in is in prefixes. So if I'm evaluating bromo versus chloro, well, bromo should go in front of chloro. B is before C. But if I have dibromo and chloro, chloro doesn't move in front of the bromo because of the di. So prefixes don't change the order of things. And so again, from that standpoint, if we ran into that situation, we would be numbering based on the bromo groups getting the lowest combination if possible versus the chloro groups. Now, if we have a carbonyl in there, doesn't matter how many bromo and chloro groups there are, we're going to number off of where the carbonyl is to give that the lowest combination. Same thing with alcohol groups. So, if we're thinking about a ranking system, you've got carbonyls at the top, they always get the highest priority. Alcohol groups would be under that. And then all of your alkane constituents would be under that as well. And that would include the halogens.
You kind of talked about it, but how do you know the difference between putting like an aldehyde at the end and just AL? Because I kind of had trouble with that on like the mastering.
So if we're dealing with just an alkane, then we can switch the ending to AL. As soon as we start throwing in double bonds of any kind, then we go to a different system with those. And so now that's not to get confused with. Those first four aldehydes have common names to them. And so if you are asked about a common name like formaldehyde, that is another place where we can use aldehyde. But understand that for the exam, unless I ask you specifically for a common name, you can use the IUPAC system. Because in a lot of ways, it's a little bit more standardized, it's a little bit easier. All right, let's look at this third example. Now, once again, we need to identify the longest chain. Since we know we have an aldehyde group here, we can automatically start numbering from this carbon. We know we're going to anyway. So the question is, what's going to give us the longest chain? Do we go just straight across, or do we try to follow one of those branches? And we can see that regardless of which way we draw it, we're going to end up with a 5-carbon chain. The only one that we got that was 4 carbons was if we followed the first branch up. And obviously that's not the correct answer because we're going to get, that's the shorter of the chains. So since we get 5 in our linear combination, we'll just go with that one. That one's the easiest to follow. And so our numbering here, 1, 2, 3, 4, 5. So we have a 5-carbon chain. That is an aldehyde. So we are dealing with a pent and al. Pentane is the chain. The aldehyde changes it from pentane to pentanal. So we already have that part established. We are dealing with a pentanal here. And again, we don't need to number it 1 pentanal because again, it's implied that's going to be the first carbon in the chain. Now it just becomes a matter of identifying those 2 side groups. They're both methyl. both methyl side groups. We've got 2 of them, so it's going to be dimethyl. And we can see from our numbering, we've got a 3 and a 4. So we're dealing with 3,4 dimethyl pentanal. All right, so Sean kind of just came in with the same question we were just talking about. So how do I know when to do al versus aldehyde? If I have a alkane, all carbon to carbon single bonds, I can change that one to Al. So that's how it becomes a pentanal. Benzene rings aren't alkanes. Benzene rings are that repeating single bond, double bond, single bond, double bond pattern. And so with benzene rings, we don't name them with Al, we just slap aldehyde on the end of it. So if I have just a normal chain of carbons, no double bonds in it, then I can just change the ending to Al. I don't have to slap on aldehyde. And this isn't one of the ones that would have a common name that we would at least be required to know. So we can't even fall back on that. And really those ones, we tend not to do this if it has any kind of branching on it. So those common names really only apply if it is just the 4 carbon chain with the aldehyde ending, or the 3 carbon chain with the aldehyde ending. If we start throwing other side groups on there, it becomes a lot more difficult to actually name them with a common system name. Okay, Olivia, I would have to take a look at your quiz specifically. 1255B, 1257B. See if I can find those. They should be out of the problem here. Chloropropionylaldehyde. Okay. So what we're looking at is see if I can zoom that back a little bit. I don't know if I can with this ebook. Okay, maybe. Okay, so no, it's not about al versus aldehyde. It's about common system versus IUPAC system. So the common system name for a 3 carbon aldehyde would be propion aldehyde, which is what is featured here in 57B, propion aldehyde. So propion aldehyde would indicate a 3 carbon chain that is an aldehyde, and then you have a chloro group in the 3rd position, which would be at the end of that chain. And as Olivia is pointing out here, that's the same structure as here in 55B. Yet in 55B, we're asked to use the IUPAC naming system. And the IUPAC naming system, we call that 3-propanal. Why are they different? Different naming systems. This is the IUPAC system compared to the common naming system. And one of the reasons we got away from the common naming system is it becomes a little bit more complicated as the molecules get more complicated. Whereas with the IUPAC system, it's easier to cover branching and side groups.
Both of those, both the common and the impact making test or.
So yes, for the first 4 aldehydes, you need to know those. And that is something that we did talk about. It's formaldehyde, acetaldehyde, propion aldehyde, and keter aldehyde. Those are the 4. And so after that, again, if you're asked about them, it's probably going to be in a multiple choice, because on the free response section where I'm asking you to name things, I'm being very broad. Give a correct name for this. Give a correct structure for this. So I'm giving you a little bit more freedom to kind of handle it however you best handle it. So in those cases, there will be multiple correct answers possible in some of those drawings. All right, so let's flip this around. We've just done a lot with turning structures into names. Let's flip this around and try to do names to structures. And so what I want you to do is, if you got a piece of paper handy, let's work on problem number 58 here. So let's take a couple of minutes. There is a mixture of common aldehydes as well as the IUPAC naming. But what I want you to do is I want you to go through and try to draw these 4 molecules. And then in a couple minutes time, we'll go through each of the answers and we'll see if we're on the right track, give you a chance to ask some more questions. So that is where is the aldehyde? It ends in AL, it's an aldehyde. So where is it?
Is it at the end?
Give a drop.
Okay.
You drop butane. Yeah. And so now we look at, so if that is the place, where's the fluoride? And so the last thing you want to always make sure that you do is ensure that all of your carbons are correctly accounted. So do I have 4 bonds? Do I have 4 bonds? Do I have 4 bonds? And then we have Cl here.
Yeah.
And this carbon, 2 bonds here, 2 bonds of hydrogen, and 1 bond of chlorine. It's 5 bonds.
Yeah. ketone always double bonded in the middle?
So you'll always have that carbonyl group, that carbon oxygen double, somewhere in the middle of the chain. That's what a ketone is. That's what separates a ketone from an aldehyde.
So if it's like, since like C, since it's 6, where would you put it? Like, does it matter where you put the double bond, because it's.
Well,
funny.
so what's that number for?
Oh, some fish.
So,
That's her.
so hex tells you that it's 6.
Mhm.
The 2 tells you where to put that carbonyl. And then obviously if the 2 is the carbonyl, you know that right next door is the methyl group, since that it's 3-methyl.
Okay, yeah.
All right, so let's see how we're doing here. So first one, formaldehyde. I have to recognize this is an old system name. Again, the old system prefixes form, acid, propion, butyr, or butyr, or however you want to pronounce that Y. So formaldehyde, I'm talking about a 1-carbon aldehyde. So I'm looking at something like this.
Is there always 2 H's on the carbon?
Well, remember, carbon always has to have 4 bonds. So if it's only 1 carbon, that means that there's not another carbon for it to link to. So if I've got 2 bonds up to the oxygen, I'm going to have 2 other bonds for hydrogen. 2-chlorobutanol, I need to recognize, okay, this is an aldehyde. We've got Al ending. Butane, butane, we're talking about a 4-carbon chain. So 2, 3, 4. That's going to be our structure. Now the fourth or first, however you want to draw it. You're going to have that group on there. So at the end of the chain, you're going to have that aldehyde group. And then that means that if this is carbon number 1, this must be carbon number 2. And that's where the chloro group would go. Now, understand you could easily draw the mirror image of that. 1, 2, 3, 4. Carbonyl group on this end, which I don't know about you, on aldehydes, it just kind of feels natural to draw the aldehyde group on the right-hand side as opposed to the left-hand side. Technically, either one's correct, and technically the structure is going to be exactly the same. Because it doesn't matter, we aren't set on numbering left to right. We can number right to left just as easily. The really nice thing about going this direction where you're drawing is if you understand kind of the structure in terms of how many carbons are supposed to be in it, that kind of thing, you get to set your own rules as far as how it's going to be numbered in terms of, do I want to number it left to right? Do I want to number it right to left? And then it just becomes a matter of counting. Okay, this is 2-chloro, so that chlorine has to be on the 2nd carbon, wherever that 2nd carbon is, based on the rules I made. For 3-methyl-2-hexanone, we are going to have to recognize ONE means ketone. So I'm going to have a carbon double bonded to oxygen. The 2 tells me the position that that's going to be in. And hexane tells me it's a 6-carbon deal. So I've got 2, 3, 4, 5, 6. 6 carbons as my chain. The double bond, the carbonyl, is going to be in the 2nd position, right there. And the methyl group is going to be in the 3rd position, right there. And again, I could easily draw it the other way if I wanted to. again, this is a personal style kind of thing. I like putting aldehyde and acid groups on the right. I like drawing pretty much everything else left to right. Just makes it's a little bit easier, just to kind of, at least for how I draw. The last one here, 3,5-dimethylhexanal. Okay, I'm dealing with a hexa, which again means 6. But this time I'm dealing with an aldehyde. So I have a 6-carbon aldehyde. 2, 3, 4, 5, 6. Again, it's an aldehyde. I'm going to draw the aldehyde group on the end here. I just have to remind myself that this is carbon 1. So when I draw this as 3,5-dimethyl, this is carbon 3, this is carbon 5. I can draw it that way. And I know exactly what I'm doing. So, I mean, to me, I think the hardest thing, other than just kind of getting all the information unjumbled in my head, the hardest thing is just kind of figuring out the organizational structure. The nice thing about drawing is that I get to kind of impose my own organizational structure on it if I follow kind of the guidelines. But aside from that, I'm not being held to whatever, you know, this drawing says it's going to be. Okay, they've drawn it this way, I have to follow it that way. All right, let's go back to some more questions.
Do reactions at some point? Like I understand like how they like when like pentanol becomes like right, but like when you did the questions like on the quiz or on the homework, it was like which one is the product? I don't like know how to do that.
Okay. So it's a little more challenging than usually like to be. All right, so let's go. Actually, I think we might, for the kind of question you're asking, that's more of a chapter 11 kind of reaction. I mean, there's a little bit of it in chapter 12 as well. But if we're trying to figure out like where does the group go, that's more of a chapter 11 kind of idea. Because if we can understand it there, we can apply it to those special situations in chapter 12. So whenever this decides to load up.
Yeah, I'm just confused on that, and then also like when it asks what you need to make this product and
Okay, so I can kind of put your mind at ease a little bit there. That's not the kind of question I'm going to ask you on the exam. I'm looking at it more from kind of a broad generic kind of standpoint. So really what you need to recognize is if you know the reactant and you know the product, you have to understand what kind of process got you there. So is it an oxidation process that gets you from point A to point B? Is it a reduction process that gets you from point A to point B? Is it an addition or a dehydration or something along those lines that gets you between the two? I'm not going to be too hyper focused on that other than just kind of knowing some more of the kind of the basic idea. So don't get too caught up in having to memorize, that potassium dichromate is a strong oxidizer, or that you need, specifically need heat and acid for this reaction. That stuff's important. And yes, as far as I will tell you that, the reaction section on the exam on Monday is going to have this undergoes oxidation. What is the product? This undergoes reduction, or undergoes, this gets exposed to H plus, gets exposed to acid. This gets exposed to, so you're gonna have to know kind of the constructs, but it's more of a recognition thing. Can you recognize from the reactants what's supposed to happen here? So from an oxidation standpoint, I'm just gonna tell you it's an oxidizer. I'm not gonna give you a specific oxidizer. From a reduction standpoint, you need to recognize, you need to know that it's a process and that involves hydrogen and catalyst. But I'm not going to get deep on, oh, well, you didn't know that nickel was a catalyst, I'm going to come after you.
Yeah, I think it was that study module we did, and it had a lot of that, and I was like,
Yeah, I think one of the things, I like the study modules a lot. Unfortunately, they kind of go a little bit too far, and I can't edit them enough to pull it back without having to, there are a certain number of questions that have to be present in order for the module to run. And so I get to a point sometimes where I've edited out so much that goes above and beyond that there's nothing left. And so I have to either not give you a review activity, which I really don't want to do, or I have to kind of hope that you can find the combination of answers in the textbook to muddle your way through those couple of problems that I couldn't edit out, and know that the heart of what I'm asking you to do is buried in that module somewhere. All right, so let's look. All right, so questions like these. So we've got two different kinds of reactions here. This first one we should recognize pretty easily. Anytime we see the reaction with hydrogen and some kind of a metal, we know that we're dealing with a hydrogenation reaction. Now in chapter 12, we call that a reduction reaction, but the idea is the same. That hydrogen, with the help of this catalyst, is going to spread itself out over the double bond. So we're going to end up with an extra hydrogen here and an extra hydrogen there. And so the net result would be cyclohexane from cyclohexene. Now, let's just say that for the sake of argument, we were dealing with a aldehyde instead. Under the same conditions, we reacted with hydrogen in the presence of nickel, we would see the exact same results. We would have an addition of a hydrogen on the carbon and an addition of a hydrogen on the oxygen. That double bond would turn into a single bond. We would end up with an alcohol. So what was called a hydrogenation reaction in chapter 11 has been relabeled a reduction reaction in chapter 12. The only difference, the reason we don't call this first one a reduction reaction also has to do with our definition of reduction involves the presence of oxygen. And there's no oxygen in that first compound. But the mechanics of it are identical. That hydrogen basically lays over the double bond and creates two new bonds and gets rid of the double bond.
In that first one where you do a little pentagon, would you have to symbolize the two hydrogens?
Nope.
Branching off.
No, because if you remember what line notation implies, it implies that any bond that's not shown is the hydrogen. So I look at those and I say, okay, I've got 5 carbons in the ring. Each carbon is bonded to 2 other carbons, which means that each carbon must also be bonded to 2 other hydrogens to give it 4 total. So the only time in line notation we show things branching off is when they're not carbon and hydrogen. That's really the only time that we'll identify. Now, I will warn you on the exam, for whatever reason, the molecule drawing software I was using always labeled the terminal carbons, the carbons at the end. So even if they were CH3s, it would take the line structure and it would just make a line and it'd say CH3 at the end. Now I'll give you instructions on the exam just to kind of ignore that. It's not a methyl group attached to this other chain. It's part of the main chain. It's just it's a funny quirk of the software that I was using, which is a lot better than the software that came with the book packages. They were not good. Like just, printed out kind of green and fuzzy. Didn't look good at all. All right, so that's this kind of reaction. Now, this second kind of reaction, where we have water in the presence of H+. H+ is acid. So in chapter 12, we saw this kind of reaction showing up as maybe H2SO4 instead of just H+. Means the same thing though. But in these kinds of reactions, what we are considering is we have to rethink what water is. We can think of water as the combination of a hydrogen and a hydroxyl group, an H and an OH. And so from that perspective, the reactions can be very similar to the reaction that we just did. That HOH is going to lay itself over the double bond. And we're going to form a new bond to H and a new bond to OH. The question becomes, what way do we end up drawing it? So this is a 1, 2, 3, 4, 5, 6 carbon chain. Do I draw it with the OH coming off of this first carbon? Or do I draw it with the OH coming off of the second carbon? Okay. This was the subject of some of the emails I got over the weekend. This is what are called Markovnikov's rules. Which one do we choose? It's going to be not this one. It's going to be this one here on the right. How do I know that? Well, what Markovnikov's rules say, and we didn't state this explicitly as Markovnikov rule, but what it says is that when we've got multiple groups attaching over a double bond, they're going to go toward their own kind. So the hydrogen is going to go to the side of the double bond that has more hydrogens on it. The OH is going to go on the side that has fewer H's on it. And so in some cases, it doesn't matter. In some cases, it does. So in this case, I'm looking at, do I make a primary alcohol or a secondary alcohol? Well, I'm gonna make a secondary alcohol because that H on the end, there are more H's on the end than in the middle. Now, if I go into the interior, it becomes a little bit more fuzzy. We end up having multiple products possible with maybe there is a preference for, 2 hexanol versus 3 hexanol, but it's probably a slight one. Whereas this one is very stark and distinct. It's probably in the high 90s% for the 2 and in the low single digits with that for the 1. There's a very clear preference for that hydroxyl group being in the interior of the chain as opposed to the exterior. Now, in the case of ring structures like this, I'm going to have an H and an OH. The location's not going to matter in this case. Because in all of these cases, I would get cyclohexanol, or excuse me, cyclopentanol, 5-carbon chain. Because there's only the one group and it's on the ring, its location is ambiguous. It doesn't matter. So as far as that's kind of concerned, I mean, that's the kind of stuff that you'd have to worry about. So, if I'm doing if I'm adding water, if I'm adding water to a molecule, I have to be concerned about where that OH group goes. Otherwise, it doesn't matter as much. If I'm adding hydrogen, it's the same either way. I just need to replace the double bond with single bonds to hydrogen. So in a case like this 66B, I've got a 1, 2, 3, 4, 5-carbon chain. This was 1 pentene. It's just going to turn into pentane. Double bond's going to go away with hydrogenation reaction. In chapter 12, the reactions that we get into have a similar kind of feel to them. So again, with reduction reactions, we can see very clearly the reduction reaction is just going to add hydrogen across that carbonyl group. And that would happen if we were dealing with aldehydes or with ketones. The only difference would be getting a primary alcohol with an aldehyde or a secondary alcohol with a ketone. The other reactions that we excuse me, that we would tend to worry about are these oxidation reactions. And remember, with oxidation reactions, we're just looking at adding oxygen bonds. So an alcohol turns into a carbonyl. And then depending upon where that carbonyl is, it can be oxidized further if it's an aldehyde, because that C to H group on the end can be replaced with another oxygen. turn it into an acid. If it's a ketone, the carbon's out of bonds. It has no more bonds to give, and so we can't oxidize a ketone any further than what it already is. The other wrinkle that gets introduced here is we can reverse the hydration reactions that we saw in chapter 11. So it's going from an alkene to an alcohol. We just talked about that kind of a reaction. Well, in the presence of heat and acid, we can reverse them and go back to a alkene. And so what you'll notice is if you go back to chapter 11, if you go back to the ones that we just did, if I wanted to take this propene and turn it into propanol, all I would have to do is add water and acid. Now, the alcohol that we would create wouldn't be one propanol, it would have been two propanol because that OH group would have slid into the middle instead of the outside. We just talked about that. But that would have been the reaction. It would have been water plus acid to create the reaction. Notice that all that's different here is we don't need the water because the water is on the molecule itself. We do need heat. We need heat to reverse the reaction because the alcohol is the more stable product than the alkene was. But basically the two reactions are opposites of each other. Kind of like oxidation reactions and reduction reactions. Oxidation reactions remove hydrogens. Reduction reactions add hydrogens. All right, we've got about 5 minutes. Any final questions? Anything else we want to kind of look at? We obviously spent most of our time in chapters 11 and 12, and with good reason. What I would remind you is don't forget that chapter 6 still exists, and it is almost 40% of the exam. It is a good chunk of it. So, it feels like we kind of got away from it because it has been it hasn't been a full month, but it's felt like a long time since we've been in the throes of that. But, we don't want to lose sight of that because we're focusing so much on the organic part of this class. So make sure you go back, work within kind of the space, and make sure that in the prep guide I put in here what that table is going to look like that you're going to get. Just make sure that you know how to use it. Go back through those modules. You can now that everything's past due, you can go back through your quizzes, you can go back through the study modules and just kind of revisit all of this chapter 6 stuff again as well. So it's real tempting because we've had such a step up in difficulty and step down in how much we just naturally understand about the organic stuff. There's going to be a tendency to want to focus just on those things. But because it's been about 3 weeks at least, we don't want to lose sight of the fact that chapter 6 is still there and it's still a decent portion of the exam for Monday. Any last thoughts, questions? All right, thank you for coming. This will get posted onto YouTube later today, so you can always come back and revisit it. And if anything comes up over the weekend, you know how to get a hold of me. Send me an email, send me a remind. I'll be happy to touch base with you. Have a good weekend.
Thank you.